Hello, everyone. Welcome to our presentation. Today, we're going to explore the fascinating topics of continuity and differentiability. This is the first slide, so I just want to start by giving you a quick overview. We'll discuss what these concepts mean, why they're important, and how they relate to each other. I'm excited to take you through this journey, so let's get started. Let's take a closer look at the mean value theorem. This is a fundamental result in calculus that connects the average rate of change of a function to its instantaneous rate of change at some point within an interval. It essentially tells us that, under certain conditions, there exists at least one point where the derivative equals the average slope over the interval. Moving on, we'll explore the exponential function. This function is crucial because of its unique properties, especially how it models natural growth and decay processes. Its derivative is proportional to itself, which makes it a key player in differential equations and many real-world applications. Next, we'll discuss the chain rule. This is an essential technique for differentiating composite functions. Think of it as a way to peel back layers of functions to find the derivative of a nested structure. Mastering the chain rule is vital for working with complex functions. Then we come to differentiation in general. It's the process of finding the derivative, which measures how a function changes at any given point. Differentiation is at the heart of calculus, enabling us to analyze slopes, rates, and optimize functions. Following that, we'll look at the differentiation of exponential and logarithmic functions. These functions often appear in various fields, and knowing how to differentiate them correctly is important. Their derivatives have specific rules that simplify calculations and deepen our understanding. We'll also examine explicit and implicit functions. Explicit functions are directly expressed as y equals something, while implicit functions define a relationship between variables, often requiring implicit differentiation. Understanding both types broadens our ability to analyze diverse functions. Next, we'll review the derivatives of certain functions. This includes common functions like polynomials, trigonometric, exponential, and logarithmic functions, each with their own differentiation rules. Recognizing these helps us efficiently compute derivatives across different scenarios. Finally, we'll revisit the concept of continuous functions. Continuity is a key prerequisite for many theorems, including the mean value theorem. It ensures the function has no breaks, jumps, or holes within an interval, allowing us to apply these important results confidently. Throughout this section, remember how these concepts interconnect to build a solid foundation in calculus. They all serve to deepen our understanding of how functions behave and change. Let's talk about continuous functions. A continuous function is one where, intuitively, you can draw the graph without lifting your pencil from the paper. More formally, at any point in its domain, the function's value can be made arbitrarily close to the function's value at that point by choosing inputs sufficiently close to it. This means there are no jumps, breaks, or holes. This property is crucial because it ensures smoothness in the behavior of the function, allowing us to analyze and predict its behavior more reliably. Continuous functions are foundational in calculus, especially when dealing with limits, derivatives, and integrals. Throughout this presentation, understanding continuous functions helps us see how mathematical models behave in real-world scenarios, where smoothness and predictability are often desired. So, when we talk about continuity, we're really talking about the seamless flow of a function's output as the input changes gradually. A function is continuous at a fixed point if we can draw the graph of the function around that point without lifting the pen from the plane of the paper. This means that, as we approach that point from either side, the function's value gets closer and closer to the value at that point. In other words, there's no sudden jump or break in the graph at that location. Continuity is a fundamental concept because it helps us understand how smoothly a function behaves. And when we talk about continuity at a specific point, we're essentially checking for these smooth, unbroken behaviors right there. This idea ties into the overall theme of understanding how functions change and behave across their domains. Let's talk about the continuity of a function. When we say a function is continuous, we mean that there are no sudden jumps or breaks in its graph. It's like drawing the curve without lifting your pen off the paper. To understand this better, we need to look at a few key ideas. First, the function must be defined at the point we're examining. If it's not, then continuity doesn't hold. Second, the limit of the function as we approach that point must exist. And finally, the value of the function at that point must be the same as the limit. If all these conditions are met, we say the function is continuous at that point. This concept is fundamental because it helps us understand how functions behave smoothly and predictably, which ties into the overall theme of analyzing and understanding the behavior of mathematical functions. Let's take a closer look at this graph. As you can see, it shows a function that cannot be drawn in one continuous stroke without lifting the pen. This illustrates a key idea about discontinuities in functions. When a function has a discontinuity, it means there's a break or a gap in its graph. You can imagine trying to draw it in one go, but hitting a spot where the line just can't continue smoothly. This is important because it highlights that not all functions are perfectly smooth or continuous everywhere. Recognizing these discontinuities helps us understand the behavior of functions more deeply and prepares us to analyze more complex graphs. So, in essence, this slide emphasizes that some functions inherently have breaks, which are crucial to identify in our studies. Let's take a look at these additional graphs. These visuals complement what we've discussed so far and help us see the bigger picture. As you can see, each graph highlights different aspects of the data, giving us a more comprehensive understanding. They emphasize key trends and patterns that are crucial for making informed decisions. By examining these, we can identify areas of strength and opportunities for improvement. Connecting these insights back to our overall theme, they reinforce the importance of a data-driven approach in achieving our goals. So, I encourage you to look at these graphs carefully, as they add valuable context to our discussion. Let's talk about differentiation. This is a crucial part of standing out in any competitive landscape. Essentially, differentiation is about highlighting what makes your product or service unique compared to others. It's not just about being different, but about being meaningfully different in a way that resonates with your target audience. When we think about differentiation, we should focus on the key points that truly set us apart, whether that's innovation, quality, customer experience, or value. These elements can help establish a strong position in the market. Remember, the overall goal here is to connect these differentiators to the broader theme of our presentation, which is about creating sustainable competitive advantages. By clearly understanding and communicating what makes us unique, we can better align our strategies and build a compelling value proposition that appeals to our customers. Let's talk about the problem we're addressing. It's important to understand the core issue that our solution aims to solve. This helps us see why this work is so critical and how it impacts our industry or community. Moving on, differentiation is key. We need to clearly identify what sets us apart from existing solutions, what makes our approach unique and more effective. Highlighting these points ensures that our audience sees the value and innovation we bring to the table. When we connect these ideas to the overall theme, it becomes clear how understanding the problem and our unique approach fit into the bigger picture of our project or mission. When we talk about differentiating f of x with respect to x, what we really mean is finding the derivative, often written as f prime of x. This process, called differentiation, is all about understanding how y changes as x changes. So when varies slightly, y also changes, and the rate at which y changes is what we call the derivative of y with respect to x. It's a way to measure the sensitivity of y to changes in x. Differentiation is the tool we use to find that rate of change. It's a fundamental concept because it helps us analyze how functions behave, how they increase or decrease, and how they respond to small changes in their input. This idea of the derivative is central to understanding many aspects of calculus and the overall theme of analyzing change. A derivative can be thought of as how much one quantity is changing in response to changes in some other quantity. It's really about understanding the rate at which things are changing. The derivative is essentially a measure of how a function changes as its input changes. So, when we talk about derivatives, we're focusing on the relationship between the input and the output of a function, and how small changes in the input can lead to changes in the output. This concept is fundamental because it helps us analyze and predict behaviors in a wide range of fields, from physics to economics. It connects directly to the overall theme of understanding change and how to quantify it mathematically. In this slide, we're going to explore derivatives of exponential functions. These functions are fundamental in calculus because they model many real-world phenomena, from population growth to radioactive decay. When we take the derivative of an exponential function, especially one with a base like e, the process reveals some interesting properties. A key point to remember is that the derivative of ex is ex itself, which is unique and very powerful. For other bases, like a x, the derivative involves a constant factor. Specifically, a x times the natural logarithm of a this highlights the importance of the natural logarithm when working with exponential functions. Understanding these derivatives helps us analyze the rates of change in various systems, making this concept central to our overall study of calculus and its applications. Let's look at some additional examples of derivatives to deepen our understanding. These examples help illustrate how derivatives can be applied in various contexts beyond the basic rules we've covered. By exploring these, we can see the versatility of derivative rules and how they connect to real-world problems. Remember, recognizing different types of functions and their derivatives is key to solving more complex calculus questions. So, as we go through these examples, keep in mind how they fit into the broader theme of understanding change and rates in mathematics. Today, we're going to discuss two fundamental operations in single-variable calculus: differentiation and integration. These are the core tools we use to analyze how functions change and to find areas under curves. Firstly, antidifferentiation is essentially the same as integration. When we find an antiderivative, we're looking for a function whose derivative is the given function. On the other hand, the process of finding a derivative is called differentiation. It's all about analyzing the rate at which a function changes at any given point. Now, the reverse of differentiation, finding the original function from its derivative, is called antidifferentiation or integration. This relationship between differentiation and integration is a key theme in calculus because it shows how these operations are interconnected. So, understanding both differentiation and integration helps us grasp how functions behave and how areas and accumulated quantities relate to rates of change. They are two sides of the same coin, providing a powerful framework for analyzing real-world problems. Let's consider the straight line y equals 3x plus 2. Now, when we're differentiating this linear function, it's interesting because the slope remains constant. Differentiation from first principles is a fundamental way to understand how the slope or rate of change works at any point on the function. Essentially, we look at the difference quotient, which involves calculating how the function values change as x changes slightly. By doing this, we can see that for a straight line, the derivative is just the coefficient of x, which is 3. This ties into our overall theme because it shows that the rate of change for a linear function is constant, making differentiation straightforward in these cases. It's a great starting point before we explore more complex functions. Let's take a closer look at differentiating a linear function. Here, we're considering the straight line y equals 3x plus 2. This is a classic example because linear functions are the simplest type of functions to differentiate. When we talk about differentiation from first principles, we're essentially looking at how the function changes at any given point by examining the limit of the average rate of change as the interval approaches 0. For a linear function like this, the slope is constant, which makes the differentiation process straightforward. The key idea is to find the derivative by calculating the difference quotient, then taking the limit as the change in x approaches 0. This process reveals the rate at which y changes with respect to x, which, in the case of a line, is just the slope, 3. So, in essence, when differentiating a linear function from first principles, we see that the derivative is simply the coefficient of x, reflecting the constant rate of change. This ties into the overall theme of our presentation, understanding how functions behave locally and how their slopes give us critical insights into their properties. Now, let's move on to slide 17, which focuses on derivatives of certain functions. Here, we're diving into some specific cases where derivatives have particular forms or properties. These derivatives are crucial because they often appear in various applications, from physics to engineering. We'll explore how the derivatives of functions like exponential, logarithmic, and power functions behave. Understanding these helps us build a solid foundation for more complex differentiation rules. Remember, recognizing these patterns allows us to differentiate more efficiently and accurately. So, as we go through this, keep in mind how these derivatives fit into the bigger picture of calculus and problem solving. Now, let's dive into the derivatives of trigonometric functions. This is a fundamental part of calculus because understanding how these functions change helps us analyze waves, oscillations, and many real-world phenomena. The key point here is that the derivatives of sine and cosine are closely related to each other, which makes sense given their interconnected nature on the unit circle. Specifically, the derivative of sine is cosine, and the derivative of cosine is negative sine. These relationships are crucial because they form the basis for solving differential equations involving trigonometric functions. Remember, these derivatives also help us understand the behavior of these functions, such as where they increase or decrease and their points of inflection. Connecting this to the overall theme, mastering these derivatives allows us to analyze more complex functions and signals, which is essential in fields like physics, engineering, and even signal processing. Let's take a closer look at the rules of derivatives. These rules are fundamental because they help us find derivatives efficiently and accurately. First, we have the power rule, which is probably the most common. When you have a function like x raised to a power, you multiply by that power and then decrease the power by 1. It's simple but powerful. Next, the constant rule states that the derivative of a constant is 0, because constants don't change. Then there's the sum and difference rule, which tell us that the derivative of a sum or difference is just the sum or difference of the derivatives, so you can differentiate each term separately. The product rule comes into play when you're multiplying two functions. It might look complicated at first, but it involves taking derivatives of each function and then combining them in a specific way. Similarly, the quotient rule helps us differentiate ratios of functions, again by applying a specific formula to handle the numerator and denominator. And finally, the chain rule is essential when dealing with composite functions. It allows us to differentiate nested functions by multiplying the derivative of the outer function by the inner derivative. These rules are interconnected and form the backbone of calculus, helping us analyze how functions change, which ties right into understanding rates of change and slopes, core themes of this presentation. All right, let's talk about the chain rule. The chain rule is a fundamental concept in calculus that helps us differentiate composite functions. Essentially, when you have a function inside another function, the chain rule allows us to find the derivative of the entire composition. It's like a way of peeling back layers to see how each part contributes to the overall rate of change. The key idea here is that you differentiate the outer function, keeping the inner function intact, and then multiply by the derivative of the inner function. This process is crucial because many real-world problems involve nested relationships, and without the chain rule, differentiating those would be much more complicated. Remember, understanding the chain rule ties directly into our broader theme of mastering how functions change and interact. It's a powerful tool that extends our ability to analyze complex functions, making calculus much more versatile and applicable. Now, let's take a closer look at chain rule problems. The key idea here is that the chain rule helps us differentiate composite functions, functions inside of functions. When you see a function like f of g of x, you're dealing with a composition, and the chain rule tells us how to differentiate it correctly. The most important concept to remember is that we need to differentiate the outer function first, then multiply by the derivative of the inner function. Think of it as peeling back layers, like an onion, to get to the core. This process is really powerful because it allows us to handle more complex functions that would be difficult to differentiate otherwise. Throughout this section, the goal is to build your confidence with applying the chain rule in various contexts, which is a crucial skill for tackling many calculus problems. Remember, understanding the structure of the function is the first step to differentiating it effectively. Now, let's delve into the concepts of explicit and implicit functions. These are fundamental ideas in understanding how functions are defined and how they behave. An explicit function is one where you can directly solve for the dependent variable, like y equals some expression in x, for example, y equals 3x plus 2. It's straightforward and easy to work with because y is isolated. On the other hand, an implicit function involves equations where the dependent and independent variables are mixed together, and you can't easily solve for one in terms of the other. Think of equations like x squared plus y squared equals 25. That's a circle. You can't just write y as a simple function of x without some additional work. Understanding the difference is crucial because it impacts how we differentiate and analyze these functions. Explicit functions are usually simpler to handle, but implicit functions often appear in more complex relationships. Recognizing whether a function is explicit or implicit helps us choose the right techniques for analysis, which ties back to the overall theme of mastering different types of functions and their behaviors. Let's talk about implicit differentiation. This technique is really useful when dealing with equations where y isn't isolated on one side, making it difficult to differentiate directly. Instead of solving for y first, we differentiate both sides of the equation with respect to treating y as a function of x. One key point to remember is that when we differentiate a term involving y, we need to apply the chain rule. That means multiplying by dx. Since y depends on x, this is crucial because it keeps track of how y changes as x changes, which is central to implicit differentiation. By doing this, we can find dx even when y is embedded within the equation in a complex way. It might seem a bit tricky at first, but with practice, it becomes a powerful tool that connects to the larger theme of understanding rates of change in more complicated scenarios. Overall, implicit differentiation extends our ability to differentiate functions beyond the explicit forms, giving us a broader understanding of how variables interact and change together. Let's take a closer look at the exponential function. This type of function is characterized by the fact that its rate of change is proportional to its current value. In other words, as the function grows, it does so at an increasing rate. This leads to that distinctive J-shaped curve we often see in exponential growth scenarios, like population increase or compound interest. One of the key points to remember is the general form of an exponential function, which is y equals a times b raised to the power of x, where a is the initial amount and b is the growth factor. When b is greater than 1, we see exponential growth. If it's between 0 and 1, it indicates exponential decay. Understanding these functions is crucial because they model many real-world phenomena that change rapidly over time. Throughout this presentation, we've seen how these functions underpin many concepts in mathematics and science, illustrating the power of exponential change. So, as you can see here, the curves get steeper as the power of x increases. This means that when the degree of the polynomial is higher, the growth becomes more rapid. The higher the degree, the greater the growth rate, and this is visually represented by the steepness of the curve. The steeper the curve, the faster the rate at which the function's value increases. This kind of rapid growth is what we call an exponential function. It's a fundamental concept because it models many real-world phenomena, like population growth or radioactive decay, where things grow or decay at a rate proportional to their current size. So, in essence, the key idea here is that exponential functions are characterized by this rapidly increasing curve, which becomes steeper as the input gets larger. Understanding this helps us grasp how certain processes can grow very quickly, and it ties directly into our overall theme of understanding different types of mathematical growth. Let's take a closer look at the differentiation of exponential and logarithmic functions. These two types of functions are closely related, but have distinct characteristics that are important to understand. When we differentiate exponential functions, such as y equals a to the power of x, the key point is that the derivative involves the original function multiplied by a constant, which depends on the base. Specifically, the derivative of a to the is proportional to a to the x itself, with the constant being the natural logarithm of it. On the other hand, when we differentiate logarithmic functions, like y equals log base of x, the process is quite different. The derivative of a logarithmic function is proportional to 1 over x, multiplied by a constant that involves the natural logarithm of the base. This inverse relationship with x makes logarithmic functions behave quite differently from exponential ones. Understanding these derivatives is crucial because it helps us analyze the growth and decay processes modeled by these functions. It also ties into the broader theme of how exponential and logarithmic functions are inverse processes of each other. Essentially, the derivative of an exponential function is proportional to itself, while the derivative of a logarithmic function involves a reciprocal of the variable. Recognizing these key differences helps us apply the correct differentiation rules in various real-world problems. Let's explore the derivatives of logarithmic functions. These functions are fundamental because they often appear in many areas of calculus and applied mathematics. When we take the derivative of a logarithmic function, we see some elegant rules emerge that simplify the process significantly. For example, the derivative of the natural logarithm of x, which is 1 over. This is a key point to remember, because it forms the foundation for differentiating more complex logarithmic expressions. Additionally, the derivative of log base of involves the natural logarithm of a, and it turns out to be 1 divided by x times ln a. This highlights how changing the base affects the derivative, and it's crucial when working with different logarithmic scales. Understanding these derivatives not only helps us in solving calculus problems, but also deepens our comprehension of how logarithmic functions behave, especially when dealing with exponential growth or decay models, or in the context of inverse functions. Ultimately, mastering these derivatives connects to our overall goal of understanding the dynamics of functions and how to manipulate them effectively in various mathematical applications. Let's take a look at some more examples to really bring these concepts to life. As you can see, these examples help illustrate how the ideas we've discussed can be applied in different contexts. They serve to reinforce the key points and show the practical side of the theory. By exploring these additional cases, we can better understand the versatility and relevance of the approach across various situations. Remember, the goal is to see how these principles operate in real-world scenarios, making the overall message more tangible and memorable. Now, let's turn our attention to the mean value theorem. This is a fundamental concept in calculus that bridges the gap between what a function does and how it behaves. Essentially, it tells us that for a continuous and differentiable function over a certain interval, there is at least one point where the instantaneous rate of change, that is, the derivative, matches the average rate of change over that interval. This might sound a bit abstract at first, but think of it this way. If you're driving from point A to point B, the average speed over the trip is a certain value. The mean value theorem guarantees that at some moment during your journey, your actual speed was exactly equal to that average. The key points to remember are the conditions: continuity on the closed interval and differentiability on the open interval, and the conclusion that at some point, the tangent to the curve is parallel to the secant line connecting the endpoints. This theorem is not just a theoretical tool. It underpins many other results in calculus and analysis, helping us understand the behavior of functions more deeply. It connects the overall change with the local behavior, reinforcing the theme that local properties can inform us about global trends. Alright, so for this final slide, I want to highlight the core idea behind the mean value theorem. Essentially, if we have a function r that is continuous on the interval a, b, and differentiable within that interval, then there's a point c somewhere between m and b where the derivative of r at c is 0. This means that at some point, the function's slope is flat, like a horizontal tangent line. It's a powerful concept because it connects the idea of the overall change in the function over the interval to what's happening at a specific point within that interval. And as we've seen throughout this presentation, the mean value theorem helps us understand the behavior of functions more deeply, especially when analyzing rates of change and optimization problems. So remember, under the right conditions of continuity and differentiability, there's always this guaranteed point where the slope hits 0, which can tell us a lot about the function's shape and behavior.